Okay, this is the first lesson in the week of April 27th through May 1st. We're done with electricity and magnetism, and we are going backwards in the book to chapter 7 and looking at universal gravitation and how Sir Isaac Newton came up with the principle that the universe is held together with a force called gravity and how he worked out the equations for that. In order to do that, though, what I like to do is take a little bit of time and do some ancient history, the understanding of what people thought prior to Newton. I think if we just jump right into Sir Isaac Newton and what he did, we can get the equation and it really doesn't mean anything. So what I want to do today is talk about the ancient view of the universe and take it all the way up to a man by the name of Johannes Kepler. The next lesson will deal with Newton's laws of gravity, and then the third lesson and final lesson of this week will deal with applications of universal law of gravitation. So let me begin by talking about what the ancient view of the universe was. The ancients would look at the stars, and in fact, they looked at the stars and watched the stars a lot more than we do. We have TV, we have movies, we have videos, we have entertainment. There wasn't much to do in the evening if you lived in 2,000 years ago, or 1,000 years ago, or even 200 years ago, than to sit outside and look at the stars and sit around the campfire and tell stories. And they knew a lot about the universe. They were much more aware of the movement of the heavenly objects than we are. And they had come up with ideas, and by about 200 or 300 AD, a man by the name of Ptolemy, in fact, I'll put his name down, Ptolemy, had combined the ideas of the ancients and wrote it in a book which is known as the Almagest. And that book gives us the ancient view of astronomy. So let me tell you what the ancient view of astronomy was. This is not in your book. This is, they might mention some of this, but not most of it. Number one, the Earth was a sphere at the center of the universe. Because of it, this type of geometry, Ptolemy's cosmology, is called geocentric. Geocentric, geo being the word for Earth. It's Earth-centered. Now, before we go on, I want to show you something. This should surprise some of you. The Earth was a sphere. The ancients did not believe, no matter what you have been taught, that the Earth was flat. I'm sorry, they did not believe that. The Almagest very clearly says that the Earth is a sphere. When Christopher Columbus sailed, he was not worried about falling off the edge of the Earth. Only uneducated people would have been worried about falling off the edge of the Earth. The people who were educated knew that the Earth was a sphere, so much so that they had measured the circumference of it. I have a book, a copy from the Almagest, and I just want to read this to you. Part number 4, and you won't be able to see this real well, but right here, number 4, says that the Earth taken as a whole is sensibly spherical, which to us would mean essentially spherical. And he says this in the Almagest: now that also the Earth taken as a whole is sensibly spherical, we could most likely think out in this way. And he goes about talking about what would happen if the Earth was flat. And he said, if the Earth is flat, first of all, the sun would rise the same for everybody, and yet we know that's not true. And he gives a whole bunch of other arguments. I just want to point it out that the Earth was not considered to be flat. It was a sphere. And it was right smack in the center of the universe. All objects revolved in perfect circles. around the Earth. Now, you may laugh at that, but if you stop this video right now and type in time-lapse star photography, you will see pictures of stars. And if it's pointed right at the North Pole, you will have time-lapse of stars going in perfect circles. Or you might see a horizon and you'll see arcs of stars going across the horizon. That is because the stars, if you take a time-lapse picture of the stars, they will move in arcs. And if you went far enough out, they would be circular arcs. I actually discovered this myself when I was backpacking, and it was a completely dark night, and I had a fairly fancy camera, and I could leave the shutter open for a long period of time. And I laid it on the ground and went to sleep, woke up in the middle of the night and turned the shutter off. It was very dark. And when I developed that film, at that time we had film, I had circles because I had my camera pointed north, and the stars were almost perfectly circular arcs. And what was really interesting, the stars were different colors. We think of the stars as all white or maybe a little bit of yellow, but there were blue stars, green stars, yellow stars, red stars. It was really cool. So if you do that, that's what they thought. All objects revolve around revolve in perfect circles around the Earth. Now, there were actually 4 different types of objects. I should almost put this the same. There was the sun and the moon. And they understood that these were relatively close to the Earth. Relative in terms of universal distances. Number 2 were the fixed stars. The fixed stars would be stars like if you look at the Big Dipper, right? It always looks the same. It always has that shape. These stars, they move in the sky because they go around in circles, but they're fixed in comparison to each other, whereas the sun and the moon would move at different rates to each other. And they considered the fixed stars to be infinitely far away. And they actually believed that they were on some sort of a crystal sphere, so that they were all the same distance away. That's why they all moved at the same rate. And then there was one other type of object called the planets. The word planet in Latin, I believe, but the word planet actually means wanderer. The planets had a little bit of a different motion. The planets move not in perfect circles around the Earth. Now, I said everything moves circular. I'll explain that in a second. I'm going to have you watch a video, but if you were watching the sky, and let's say every night you looked at the stars in the sky, and then you were to look and say, where is, say, Mars? Well, Mars might be right here, and then the next night it moves, and it moves, and it moves. It doesn't move with the other stars, so they knew it had to be closer to the Earth. And then all of a sudden something weird will happen. Mars will actually start going backwards in the sky, and then it will move forward again. So that if you plotted its motion would do something like this. When it's going backwards, we call that retrograde motion. Retro meaning backwards, retrograde. And there had to be some explanation for that. Well, here was the explanation. It's really clever. They said, here's the Earth, right here, and here is the orbit of Mars, let's say. But rather than they thought everything had to be in perfect circles, but they knew that Mars wasn't moving like that, so what they said is, well, maybe Mars is a circle on top of a circle, so that Mars's orbit is moving like this. And if you think about what's going to happen then, the motion of Mars as it moves is going to make some sort of a weird path. So Mars is right here, then it moves and it moves to here. It actually, this has 2 motions associated with it. And what you'll get is the type of motion that would explain what's happening with the planets. Now, I have two videos, actually 3 videos that go along with this lesson. Part of the reason we're only doing 3 lessons this week. One will talk about something later, but there's 2 of them that will talk about explaining retrograde motion. One from a non-Ptolemaic viewpoint, one from Ptolemy's viewpoint, and explain what's happening. Some of you may have in the past played with a spirograph. If you had a spirograph, it was circles inside of circles, and they make interesting patterns. That's what was taking place here. Now, this was believed all the way up until, I have to see my time frame here, up until the 1500s. Something happened in Europe after the fall of the Roman Empire, and that is that we went into what is called the Dark Ages. And the Dark Ages are not dark because there wasn't light, there wasn't knowledge. When Charlemagne, excuse me, when Charlemagne became king of France, he looked around to see if anybody in France knew Latin. And nobody in France knew Latin. He wanted to learn Latin, so he had to send away to Rome to find somebody who could come and teach him Latin. My point is that knowledge disappeared. Well, prior to that, the astronomers found that although their model of where Mars should be was pretty close, it wasn't perfect. And so they constantly were tinkering with their model. I had a grandma she's gone now, but had a grandma who had a watch, and it was a wind-up watch. And it was off by about 2 minutes per day. So you know what she did at the every night before she went to bed? She reset the watch. And so it always was fairly close. But let's say she went for, say, a week without resetting her watch. The watch would be about 15 minutes off. If she went for a month, it would be an hour off. If she went for 6 months, it would be 6 hours off. It would be saying 3 o'clock when it was really 9, and so on. What happened was when Europe fell into the Dark Ages, people stopped resetting the solar system. And all of a sudden, they realized that all of our equations telling us where the planets should be are wrong. And the Pope, at that time, approached a man that you've probably heard of by the name of Copernicus, and said, could you fix what the problem is? So Copernicus began looking at all of the data, and he began to come to a different idea. And his idea is called the helio meaning sun, heliocentric universe. Now, what Copernicus says is the sun is at the center. All of the planets are going around the sun. This is the Earth here. And the moon would be going around the Earth. And then all of the fixed stars, which are infinitely far away, would be out here. By the way, this perfectly explains why we have retrograde motion, and I'm going to let the video do that. I don't have time to do that for you right now. Copernicus died, and on his deathbed he got his book, which was on the revolution of the planets, that was championed by Galileo, and Galileo actually got in trouble for it. Galileo was absolutely convinced that not everything went around the Earth, because he had looked at Jupiter and saw moons of Jupiter going around Jupiter. And he felt that the Ptolemaic system wasn't very good. So Copernicus postulated this. Now, here's where the history books go wrong. It turns out that Copernicus's viewpoint, although simpler than Ptolemy's, did no better at predicting where the planets would be than Ptolemy's did. There was an error in it, and the error comes down to the shape of the orbit. There was a belief that the circle was a perfect shape, and therefore God would make the entire universe out of circles. This leads to a man by the name of Kepler. There's another man, but I'm going to skip him for right now, called Tycho Brahe. He'll be in a video that you watch. He's really famous for one thing, and that is that Kepler took his data and used it. But there's a man by the name of Johannes Kepler, who in 1601, he was born way before that. I don't have his dates, but they're in the book. In 1601, he inherited or stole, depending on who you're talking to, some very accurate data. And he was Copernican, but he knew there was a problem with Copernicus's model, because it wasn't giving the right answers. It wasn't telling us where the planets should be at any point in time. And he began to study the orbit of the different planets, and specifically he studied the orbit of Mars. And and Kepler, after studying this for about 20 years and hundreds of pages of calculations, came up with a modification to Copernicus. And these are known as Kepler's 3 laws. The first law is this. He said that the paths of the planets are ellipses with the sun at one focus. If you take 2 points, put a string around them, and like 2 thumbtacks, we would do this in class, and I should have had this, and draw it around, you'll get what's called an ellipse. This point is called the focus. 2 points are called the foci. The sun is right here, and what we would say is that planets move around in this path. Now, it turns out that the paths of the planets are so close to being circular, you wouldn't be able to tell the difference. And in fact, when Copernicus first proposed that the paths of the planets were ellipses, people said, well, they're so close to being circles, you can hardly tell the difference. Why aren't they just circles? And Copernicus had an interesting answer. He said, if God had intended, it's not exactly his words, but if God had intended for the orbits to be circles, they would be perfect circles. The fact that they're not perfect circles means God didn't want them to be circles. The video I'm going to have you watch on Kepler, did I say Copernicus? What Kepler? Kepler's comment will portray him quite differently, but he was actually very religious. When he wrote his book explaining this, he would break out in hymns to God for having allowed him to discover this. So the first one, the paths of the planets are ellipses with the sun at one focus. The second one says that planets sweep out equal areas in equal times, which is another way of saying this, is that planets speed up when they get closer to the sun. So the idea would be this. Let's say we went for a month and the Earth went from here to here, or a planet. There's some area here. We'll call this area month number 1. If that same, there's a lot of area here. If that same planet is over here, it's going to have to move like this for there to be the same area here as here. So the second one is that the Earth actually speeds up, or a planet speeds up as it gets close to the sun. And then the third one is the really bizarre one. He said that if you take the cube of the distance, the radius of the planet from the sun, that would be its average, divided by the period squared, you get a constant. In other words, if I take t squared divided by r cubed, where r is the average length. By the way, most of these are closer, but it doesn't matter. What we do is say, what's the radius between here? That this gives you a constant. Always the same thing. And that is an amazing discovery. And I'm going to stop there with one little thing that I want to tell you. I actually grew up. My grandmother was a Kepler, and she was from the same region of Germany that Kepler was from. And I grew up being told that I was Kepler's great grandson. And then a few years back, my aunt decided to do a genealogical search. It turns out that Kepler's, I'm not directly related to Kepler, but if you took Johannes Kepler, he had a brother, and of course then they had their dad up here. Johannes Kepler's line goes this way. I'm part of the brothers line. So Johannes Kepler is my great uncle. But my grandmother, who was not, didn't know much about science or math, she was very proud of Kepler. Germans who claim him as being pretty amazing, and he was. He's considered to be perhaps the, if you rate mathematicians, Kepler will often be rated in the top 5. What he did was very mathematical. So actually with this, I have 3 videos I want you to watch. 2 of them are kind of paired. The third one is a little bit longer, and it takes you through how complicated it was to come up with Newton's 3 laws. And it's pretty impressive what he did. So there's no problems from this section. It'll be discussions. We're going to discuss the 2 videos together, and then we're going to discuss the other video, the one on Kepler's 3 laws is the name of the video. And that'll be it for this lesson. I know this has gone a little long, but that's actually quite a bit of material. It usually takes me several days in class to cover that. So we'll come back and talk about what Newton did with this, and then the applications that come out of that for our 3rd lesson.